Hey everybody, I'm going to go through the answers to these 10 initial rates questions. I've put a link to the questions in the description for the video, so if you wanted to grab a copy and maybe print them out, have a go at the questions first, then that would be great. And then obviously play this for the answers. Okay, so the first question is quite a straightforward one. We've only got one reactant. We've got to pretty much do the same for all of these questions, work out the order with respect to the reactants, with evidence obviously, work out the rate equation, work out the rate constant value and give the units for the rate constant. So all of the questions follow the same sort of pattern, but they gradually get more complex. Okay, so the first one, only one reactant, so basically we just pick two experiments and see how the initial concentrations changed and then what's happening to the rate. So and I always get my students to sort of put little annotations on the table and then talk about it in the written space underneath. So what's happening here to the initial concentration? It's halved to go from 3 to 1.5, as you'll see here. It's sort of decreased by a half. The change in the rate, well, that's also halved as well. So it's essentially doing the same thing. The rate's doing the same thing as the concentration change, and so therefore it's first order with respect to N2O5. So we'll just write that up here. And you don't have to write a lot. You literally would just go in square brackets, the concentration N2O5 times a half, rate times a half, therefore first order with respect, WRT is fine, to N2O5. Okay, so that's how I would phrase that. And obviously if you've got these annotations in the table there, the examiner knows which experiments you've used to get that from. So now we can write the rate equation. So rate equals K, concentration of N2O5. And then we're going to rearrange so that we can solve for K. So K equals rate divided by N2O5 concentration. And I'm just going to use the first row of results. So the rate for the first experiment is 3.15 times 10 to the 5 divided by 3, and that comes out at a numerical value for K at 1.05 times 10 to the 5. So moving on to the units for K now. So all I'm going to do is I'm going to look at the units for these terms here, because K was calculated by rate divided by concentration of N2O5. So the units of K are going to be the units put into that expression. So the units of rate, moles per decimeter cubed per second, divided by moles per decimeter cubed. Then we cancel the moles per decimeter cubed. So the units of K are seconds to the minus 1. Okay. So question number 2 now. So you can see we've got two reactants here. So this one's a little bit trickier because ideally, now you can't always do this, and I'll show you some examples where you can't, but ideally, if you can hold everything but one concentration constant, then the change in that concentration will be affecting the change in the rate. So you can see the order from that. So if you look at experiments 1 and 2, the NO concentrations staying at 0.001 for both of them. So what's happening to the O2 concentration? It's gone up by a factor of 3. What's happening to the rate? So these numbers aren't as straightforward as before. So all you need to do is just divide the big number by the small number to see the increase. That's a threefold increase as well. So therefore, it's first order with respect to O2. So we'll just write that in. So from experiments 1 and 2, the O2 concentration times 3 rate times 3, so it's doing the same thing. Therefore, the order with respect to O2 is 1. Okay, or first order with respect to O2, you could say. I'll just change to a different colour pen, so for the next one. So to get the order with respect to NO, if we use experiments 1 and 3 now, you can see that the O2 concentration is held at 0.001. So the increase in the NO concentration is going to be affecting the rate, but the O2 is staying the same, so it's not having any effect on the rate. So what is that factor increase? So big number divided by small number, that's a 4-fold increase. So when the NO has been doubled, the initial rate has effectively gone up by 2, the doubling 2 to the power 2. The power 2 is the order. So it's second order with respect to NO. So from experiments 1 and 3, the NO times 2 rate times 4, therefore order with respect to NO is 2. So we can write the rate equation now. So rate equals K O2 times the concentration of NO, but we need to square that one because it's second order. Rearrange for K, so K equals rate over O2 times NO squared, and I'm going to use row 1 here. So that is rate for row 1 was 1.82 times 10 to the minus 6 divided by, let's just get those, they're both at 0.001. So 0.001 times 0.001 squared. And that comes out at 1,820. So the units of K, so the units of rate on the top, so that's moles per decimeter cubed per second. The units of the concentrations on the bottom, but remember we've got to square the NO, so effectively we've got moles per decimeter cubed. You can either do moles per decimeter cubed squared, or sometimes students like to just see everything written out. So moles per decimeter cubed squared is literally just writing 2 side by side. Now we can cancel 1 moles per decimeter cubed on the one on the top with one of the ones on the bottom. So what we're left with is seconds to the minus 1 on the top divided by mole dm to the minus 3 squared effectively. Okay, so tidying that up, the moles squared is obviously mole squared, dm to the minus 3 squared is dm to the minus 6, and then basically when we take everything up to the top we flip the sign of the power. So I'm going to rub this out and just put the units in. Okay, so it would be, technically you're supposed to write the positive powers first, so it's dm6 when that dm to the minus 1 over dm to the minus 6 comes up to the top, dm to the 6 mol minus 2 s minus 1. Okay, so number 3 now, we've got 2 reactants again, so same as before. Can we see a pair of experiments where only one of the reactants is concentrations changing? So you can see in 1 and 2 the ICL is staying at 0.2, whereas the H2 concentration has doubled. What's the rate doing? It's actually going up 4-fold. So it is second order with respect to hydrogen. So I'm just going to put second in there. But obviously you would word it from experiments 1 and 2, the H2 concentration times 2, rate times 4, therefore second order. Just sort of trying to speed things up a little bit for you. For change colour, so you can see experiments 1 and 3, hydrogen's staying at 0.1, whereas the ICL is doubled. And what's happening to the rate? 0.042 to 0.084, that's a twofold increase as well. So this is first order because it's doing the same thing. Okay, so we can write the rate equation now. So rate equals K, ICL, order 1, remember, H2 is second order, rearrange for K, rate over ICL, H2 squared. Put the numbers in, I'm using row 1, so we've got 0.042 divided by 0.2 for the ICL times 0.1, but that's got to be squared. So that gives us a numerical value for K at 21. And the units, so you can see we've got the units of K are going to be rate over moles per decimeter cubed times moles per decimeter cubed squared, which is exactly what we had in that one. So I'm not going to bore you with how do we work out the units, I'll just write them straight in now. So that's dm6 mol minus 2, s minus 1. Okay, so number 4 now, so you can see it's getting more difficult in the sense that there's an extra reactant to worry about. So where can we keep 2 of the reactants constant but then only change 1? Well, 1 and 2 you can see that the Br minus is staying at 0.1, the H plus is staying at 0.1, whereas the BrO3 minus is changing. So that's what we'll look at first. So that's a twofold increase. Nice easy one to do in your head. 1.2. Don't forget about, now I'm going to highlight this because that, when I use this with my students, that catches students out a lot. So the initial rates are all times 10 to the minus 3. So 1.2 times 10 to the minus 3 up to 2.4 times 10 to the minus 3 is a twofold increase. So the order with respect to BrO3 minus is 1. So where will I put that? I'll just see if I can, hopefully that will stand out there. Okay, next one. So I'm looking at experiments 1 and 3. So why have I chosen those? BrO3 minus is constant, H plus is constant, and Br minus is trebled. So we'll use blue. So that's a threefold increase. What's happened to the rate? It's gone 1.2 times 10 to the minus 3 up to 3.6 times 10 to the minus 3. That's also a threefold increase. So Br minus is also first order. Right, so how do we get the H plus? So which pair of experiments shall we look at? 2 and 4 I think I've got, yeah, 2 and 4. So it's 0.1, 0.1 for the Br minus, 0.2, 0.2 for the BrO3 minus, whereas H plus is the only one that's changing. So we'll use that one, times 2. I have to do this. So 2.4 times 10 to the minus 3 up to 9.6 times 10 to the minus 3. That's a fourfold increase. And so therefore the H plus is order 2. Right, so we now can write the rate equation. So rate equals K. It was Br minus order 1 times H plus order 2 times BrO3 minus order 1. Okay, so leave that as with no power on. And now rearrange for K. So rate over all of that lot, Br minus H plus squared, BrO3 minus, and then substitute in all of the numbers, and don't forget about this 10 to the minus 3. I'm just going to give you the answer now. So it came out at 12, I used row 1 as usual. So if we move on to the units now, we haven't seen this one, so I'll quickly go through this. So what have we got on the top? We've got moles per decimeter cube per second for rate. We've got 1, 2, 3, 4 lots of moles per decimeter cube because that one's squared. So effectively we've got moles per decimeter cubed per second on the top. I'm just going to do one lot of moles per decimeter cubed and then put a power 4 on. Okay, just explain that again. Moles per decimeter cubed times moles per decimeter cubed squared times moles per decimeter cubed is moles per decimeter cubed to the power 4. So effectively, when we cancel that, we can knock that down to a 3. So we've got 1 over moles per decimeter cubed. So when that all goes up to the top, you get dm to the 9 mol to the minus 3 s to the minus 1. So they would be the units for that rate constant. Okay, so number 5 now. So the initial concentration, if you look at 1 and 2, or the first 2 rows, there's no experiment numbers here, you can see that B is staying at 0.1, whereas this one has gone up by 1.5. So what's happening to the rate? It's actually gone up by 1.5 squared times, okay? It's gone up 2.25 times. So one thing you can sort of do, there are only 3 orders you need to worry about: 0 order, first order and second order. So you ask yourself, right, that's changed by a factor of 1.5, so it's either going to go up 1.5 to the power 0, in other words it's going to go up 1 times and therefore stay the same. Well, it hasn't done that. It could go up 1.5 to the power 1 times, so in other words it's going to go up by a factor of 1.5, but it's done more than that. So it's got to be the 1.5 squared option. So when you divide that by that, you actually get 2.25, which is 1.5 squared. Okay, so that's telling us that A is second order. The next one is we're going to look at which experiments can we use for this one. We can use 1 and 3. So it's the A is staying at 0.1. So let's have a look at what B's done. B has doubled. The rate hasn't done anything. So where can I put my blue arrows there? So it's not times 0, it's times 1, isn't it? So effectively it's the twofold increase raised to the power 0 gets that 1 times increase. Okay, so the order of B is 0. So therefore the rate equation will look like this. K A squared, rearrange for K, so rate divided by concentration of A squared, and then using row 1 I'm getting a value for K at 273. The units of K, that goes down to 1. So in other words, it's seconds to the minus 1 divided by moles per decimeter cubed, and then bringing everything up to the top we get dm3 mol minus 1 s minus 1. Okay, right, so question 6 is where it starts getting trickier. Okay, so there's various ways you can process questions like 6. Alright, so I'll show you how I've done it and hopefully it'll all make sense. Right, so there's a couple of straightforward ones to do. So if we look at experiments 1 and 2, you'll see that A is constant and C is as well. Okay, So we can get the order with respect to B fairly easily. So that's a twofold increase, and the rate has gone up 4 times 4. So B is second order. Okay. Go to blue. So experiments 2 and 3 now. You can see 2 and 3, C concentration staying the same, B concentration staying the same, whereas A's concentration is halved. Okay, so we'll put that in. So going from there to there, that's a halving. What's happening to the rate? 8.64 times 10 to the minus 7 down to 4.32 times 10 to the minus 7. That's a half. So this must be order 1. And this is where it starts getting tricky, because the problem is we can't keep A and B constant to get C on its own. So we've got to actually vary one of the ones that we know. So what I've done is I've gone for experiments 1 and 4. Okay. And the reason I've chosen that one is because B is staying at 0.003. Okay. So you find an experiment where, you know, one of them is kept constant at least. So, okay, so 1 and 4 we're going to use. So the way I'm sort of phrasing this one, I'll do this in black. So from experiments 1 and 4, what can we see? We know that the A concentration has trebled, so it's gone from 0.001 to 0.003. We can see that the C concentration has halved, and we can see that the rate has gone threefold, a threefold increase, 2.16 times 10 to the minus 7 up to 6.48 times 10 to the minus 7. That's a threefold increase. And remember, we already know the order with respect to A is 1. Okay, so what we can say is the change in rate is equal to the change in A concentration raised to the power 1, because we know that it's first order, multiplied by the change in concentration of C raised to the power, well, we don't know that at the moment. Okay, we know that the change in rate was 3. We know that the change in the A concentration was 3, and that's power 1 because it's first order. Change in C was a half, and that's raised to an unknown power at the moment. So basically, what does that question mark have to be to give us this answer of 3? This answer here needs to be 3. Well, 3 to the power 1 is 3, so really we want to be multiplying 3 to the power 1 by 1. So that needs to be 0 order. So therefore, question mark equals 0 order. Okay, I'll just show you that that works. So if I rub that out, put the 0 in, okay, so 3 to the power 1 is 3, times a half to the power 0 is 1, 3 times 1 is 3. So that's how that works. So after all of that, we now know that C is 0 order. Okay, so we can go to the calculation now. Rate equals K, A concentration times B concentration squared, and when you rearrange and put the values in for row 1, I'm just going to go straight to K equals 24, and the units would be dm6 mol minus 2 seconds to the minus 1. So this is another one where you can't keep one of them constant. So and we've got to sort of do a similar thing to what we've just done. So let's look at, first of all, experiments 1 and 2. You can keep B constant. So this is a threefold increase for A times 3. What's the rate doing? Remember, when the numbers are tricky like that, just do the bigger number divided by the smaller number. That's actually a 9-fold increase. So obviously the 3 is being raised to the power 2 to get the 9, so that's second order. And the experiments I've used to get B, I've used 1 and 3. You don't have to use them, you could use 2 and 3 if you wanted. I'm going to go for 1 and 3. So I'm going to write this out. So from experiments 1 and 3, so we can see that the A concentration gone from 0.12 to 0.72, that's a 6-fold increase. And we can see that the B concentration has gone up by a factor of 2, 0.15 to 0.3. The rate, big number divided by small number, has gone up by a factor of 36. Okay, so that increase in rate, that 36, has been brought about by a 6-fold increase in A. Remember, it's second order, so 6 squared, multiplied by that 2-fold increase in B raised to an unknown power. So just ask yourself, 6 squared is 36, so we need that to be a 1, so it's another 0 order, isn't it? So therefore the unknown order, the order for B is 0. So we've got that, we've got that there. So now we're at a position where we can write out the rate equation. So rate equals K, it's literally just A squared. Sorry, my square brackets are looking terrible there. And then when you rearrange that and sub in the values for row 1, I got a value K it being 0.0222, and the units are dm cubed mol minus 1 seconds to the minus 1. Okay, next one. So it's another one of these trickier ones. So what can we do first of all? Experiments 1 and 2, you can see the iodine is staying at 1.25 times 10 to the minus 2. So let's get the order with respect to hydrogen. So what's that increase? That's a 3-fold increase. What's the rate done? Big number divided by a small number. That's also a 3-fold increase. Hydrogen is first order. So now for the tricky one where we can't keep the hydrogen constant, we'll go into, I'm going to use experiments 1 and 3. So what we're going to say, well, from 1 and 3, we can see that the hydrogen concentration has increased 2-fold. The iodine concentration has also increased 2-fold. The rate has increased by a factor of 4, 8.44 up to 33.8 times 10 to the minus 6, obviously. Okay, so that 4-fold increase in the rate is being brought about by that 2 to the power 1 multiplied by 2 to the unknown power. So 2 to the power 1 is 2. So what do we need this to be? It needs to also be 2 to get the 4. So therefore, question mark must be a first order 1. Okay, and that'll give us the 2 there we need to get the 4 at the end. So it's first order with respect to iodine as well. So we'll just rattle off the rate equation. K hydrogen, iodine, and then sub in the value, rearrange and substitute in the values from row 1. I got K to be 0.0643, and the units dm cubed, mole minus 1, seconds to minus 1. Second last question. It's great, great news. Probably getting a bit sick of these by now, but keep going. So this one's a bit different because it's actually, we've got to fill in the table. Okay, so we know the rate equation. So not seen this before. So in all of the questions so far, we've had to work out the rate equation from the orders. We know the rate equation, so we know the orders. Okay, so what we're going to do here is I'm going to look at experiments 1 and 2 because obviously I want to know what this blank is here. So from 1 and 2, what can we say? So let's look at the increase in the rate first of all. The increase in rate is 1.5 up to 6. That's a 4-fold increase, isn't it? The B concentration, remember this is first order, that's times 2. So we need to work out what the new concentration of A must be in experiment 2. So I've said from experiments 1 and 2, that increase in rate of 4 is equal to that unknown concentration for A raised to the power 1, because first order, multiplied by that 2-fold increase raised to the power 1. Okay, so effectively we need, if we need the answer to be 4 for the sort of the product of the question mark to the power 1 times 2 to the power 1, then question mark needs to be 2. So in other words, the concentration of A needs to be twice what it was in experiment 1. So it's going to be 0.6. Okay, so moving on to the next blank. So that's the concentration, for B for experiment 3. So we'll look at rows 1 and 3, experiments 1 and 3. You can see that the rate has gone up 6 times and the concentration of A has gone up 1.5 times. So let's feed that in. So from 1 and 3, a 6-fold increase in the rate has been brought about by a 1.5-fold increase for A raised to the power 1 multiplied by an unknown increase raised to the power 1. So we need, therefore, the question mark needs to be 4. So 1.5 to the power 1 is 1.5. If you multiply that by 4, then you're going to get 6. So the concentration of B needs to be 4 times what it was for experiment 1. So that is 1.2, isn't it? 1.2 moles per decimeter cubed. And the final one, the initial rate now. So using experiments 1 and 4, I'll just use a black pen. From 1 and 4, the increase in rate we don't know, that's what I want to try and find out. So an unknown increase in rate has been brought about by 0.3 up to 0.9, it's a 3-fold increase. So 3, but it's first order, 3 to the power 1 times 0.3 up to 0.6 is a 2-fold increase, and that's to the power 1 as well. So 3 times 2 is 6, so therefore question mark is 6. So the new rate will be 6 times experiment 1's rate, and that comes out at 0.09 moles per decimeter cubed per second. So we'll just finish this one off by working out the rate constant. So rate equals K, remember we were already given this. And using row 1, I'm getting K coming out at 0.167, and the units dm cubed mole minus 1 seconds to the minus 1. So moving on to the final question, we've got same sort of thing as before, where we've got to fill in the table. We've got the rate equation, which you can see I've already highlighted. So first blank, the initial rate for experiment 2. So let's look at what's happening. The initial concentration of P is halved, and the initial concentration of Q is a third of what it was. Okay, so let's feed that into the rate equation. So it's going to be the unknown rate will be half to the power 2 times a third to the power 1. Yeah. So that effectively is a 12th. So the initial rate for experiment 2 will be a 12th of what it was for experiment 1. So that's going to be 4 times 10 to the minus 4. So to get the next blank, so it's the initial concentration for Q, I'm using 1 and 3 because we've got all the data in row 1, so that's why I'm choosing that one. So what's happening? We've got, what's the increase in the rate? That's a twofold increase in the rate. I'm just going to do my jottings up here. So that's a twofold increase in the rate. So what's happening to P? P has doubled. So 2 to the power 2, because it's second order, multiplied by an unknown increase in concentration to the power 1. So basically 2 equals 4 times what? That's times a half, isn't it? So the concentration of Q has to be half of what it was in experiment 1. So it's 0.15. Okay, so the final one, just rub this out so I've got some space. So the final one, we've got we'll work out the initial concentration of P for experiment 4. So I'm using experiments 1 and 4. So what's happening to the rate? It's gone from 4.8 up to 19.2 times 10 to the minus 3, so that's a fourfold increase. And that's been brought about by an unknown increase in concentration for P raised to the power 2, so question mark squared, times 0.3 up to 0.6, that's doubling, isn't it? So that's 2, but first order to the power 1. So really we need this here to, when it's squared, to equal 2. So we get 2 times 2 equals 4. So the unknown thing has to actually be root 2. So root 2 squared is 2. So the initial concentration of P for experiment 4 is going to be root 2 times what it was for experiment 1. Okay, so it comes out at 0.28 moles per decimeter cubed. And then we'll just finish off by working out a value for K. So we've got the rate equation, we'll just rearrange that straight away. So K equals rate divided by the concentration of P squared times the concentration of Q. I'm subbing in the values from experiment 1 and I'm getting a K at 0.4 and the units are dm6 mol minus 2 s minus 1.